faster. There are still people logging in, but I think we only have 2 hours, so let's start. Yeah, welcome everyone to InCTRL's pre-Weftec workshop. So Weftec is virtual this year, as everyone knows, and we got a couple of requests. So we did do that workshop typically as a full day in-person workshop on Fridays before Weftec. The good news is that we have over 100 people who signed up, so much more than we typically have. So we typically have 25, 30 people in these workshops. We thought 2 hours is the maximum we can make you suffer. So we decided to keep it short, and I should actually stop too much. My name is Leif Rieger. I'm the CEO of InCTRL Solutions, and today's 2-hour virtual workshop is on identifying and hopefully overcoming process control challenges at wastewater treatment plants, or how we now call that, water resource facilities. With that, next slide. Manel, next slide. Okay, so with that, I would like to introduce the speakers. So we have our CTO, Oliver Schraar. He's around forever, so longer than I'm around. We are the same age, but I guess I spent too much time in school. Yeah, so he's an expert in all kinds of things related to data, to, of course, modeling and simulation. And he spent a lot of time during the last couple of years going very deep into modeling aeration systems. And that is also something he is presenting today. Alex is unfortunately out, so not something we can offer today. He got a little baby daughter, and he's on paternal leave, so he will not join us today. And then we have Ivan Miletic, our data analytics leader, presenting some of our work and solutions to overcome some of the technical issues in process control. With that, I'm very, very glad that we were able to have somebody from a utility reporting on practical issues they are facing and some of the solutions they developed. That is very, very important for us to actually have somebody who's able to report from the ground, who's involved in daily operation. And I'm quite happy to have Ryu Suzuki talking about process control challenges from a utility point of view. Ryu is with DC Water and is a process manager there, right? So I'm very, very glad that he agreed to join. And I'm very much looking forward to his presentation and then also to the discussions. So we try to keep the presentations short. We will always start the sessions with a little bit of a survey. So we have Mentimeter, and Manel will show. Just give me a second on the other slide, on the program, Manel. Manel, can you go back to the yeah, exactly. So we will start the session with a Mentimeter, a little survey. Then we will have the presentation, and then we go into a round table discussion. There's only a virtual table, of course, but we try to have enough time for discussion. The sessions are on problem statements, so that is the utility perspective. Then we go into using tools to do an in-depth analysis of, so the focus here is aeration control and design, right? So coming up with ways to better design the different parts of a control system. So making sure that process, sensors, equipment, and control work together. And that's the essential part here, that we need a more holistic view to make things work. Very important. The last is, we call that solutions, and that is Ivan and Marsa presenting some of our methods, findings, and solutions. And then hopefully we have some hot discussions on the topic. Yeah. With that, Manel, can you go to our survey? Okay, so what I would like you to ask is, and if you can, use your mobile, your cell phone. So I will do the same. Open a browser and type in what you see at the top, www.menti.com. It will ask for a code, and then type in that code. So I hope that, yeah, I see that people logged in. So that gives me a good indication that people used that before. I'm still trying to submit. Okay, I'm in there as well. So very good. So we have a couple of people signed in. Again, so we recommend to use your cell phone. You can also open that on a second screen that you can follow the presentations. We typically use our smartphone, right? So www.menti.com. And then the code it's asking for is 9402852. Okay. With that, let's jump into the first question, Manel. Okay, so the first question is, what are your main process control challenges? So we have a selection menu there, and you should pick some of them. For consultants or people from academia, I would recommend that you go back to the last project you had and pick one or multiple one. Yeah, so there are the first survey results coming in. Very interesting. So let's give it some time. Very good. Nobody says, I don't know, it just doesn't work. I was expecting that somebody would click that. Okay, so we have 20 people who voted already, so that's quite yeah, that's good. Most of you actually are on Menti and are doing that survey. Very nice. So you hear that all the time. So census is still very high on the list. With 9 people so far picking that. Data quality, we separated the two just to make sure that we focus on the work to be done to keep the sensors working, but really making sure that they are accurate. That's another tricky thing. Equipment limitations, also very interesting. So that's input for Rio. Maybe he can talk about that at the end. Operator training, that's a surprise. I was expecting that some more people would say, yeah, we have an issue with making sure that we train our operators. Good, very good. Next question. Okay, so the next question is, how many of the following sensors or analyzers are installed at your plant? We focus mainly on nutrient sensors. We had thrown in pH as well, but yeah, would be good to get some idea what you have installed. You're supposed to click somewhere. I don't see numbers yet. Okay. Somebody has plenty of TSS probes and plenty of flows. Oh, that's interesting. That seems to be a plant with a lot of flow meters. Okay. Yeah, we see that ammonia sensors are coming. I think I wait until we have some more. Ah, okay, good point. Yeah. So there was a response from the one with the flow meters, and that was not just water or sludge flow, that also included air flows or gas flows. So that might even be digester gas flows. Good. It sounds like flow and dissolved oxygen. That seems to be everywhere, and plenty of them. So the average being slightly under 10. Good. And then followed by ammonia. No, sorry, TSS, ammonia, then nitrate, and phosphate. We still have to work on, I guess. Good. With that, I would like to invite Rio to give us his view on utility challenges in terms of process control.
Okay, thank you, Live. Can everybody see my screen? I'm trying to put it on the slideshow mode.
Yes.
If it works. Okay. All right, awesome. All right, so my name is Ryu Suzuki. I work as one of the process engineers at Blue Plains Advanced Wastewater Treatment Plant in Washington, D.C., United States. So a lot of the challenge that I'm going to be talking about is specific to our plant, but hopefully other practitioners are able to learn from some of the challenges that we face on a day-to-day. So during this presentation, I'll just quickly give you a brief background on our plant and some of the drivers for implementing these control systems. And then one of the biggest headache with any of these controls is making sure the sensors and pretty much all your INC equipment is properly maintained. And even with a good INC equipment, we still have some of the just basic system and physical constraints that sometimes prevent us from fully achieving a good efficiency or effectiveness. And finally, at the end of the day, no matter how great the control system is, nothing is foolproof, and you always need good operators to kind of monitor and watch over the system. So those are some of the key points I'll be talking about in this brief presentation. So just something about our plant. Our average flow is 300 mgd. It's designed for 384, and I apologize for a lot of the rest of the world that do not use these numbers or the units. Hopefully it still makes sense. And then we have a very stringent total nitrogen limit. So it's based on how many pounds or how many kilograms of nitrogen we could discharge into the outfall. And it's basically equivalent to 3.8 milligrams per liter at our design flow. So in order to reliably achieve that, we set a pretty ambitious nitrogen removal target. Around more or less 1 milligram per liter on the nitrate, non-detect on ammonia, and there's always that pesky TKN, the organic nitrogen. It's always there. We can't really do too much about it. And just kind of stepping back a little, maybe some of the issues that we could talk about in the discussion is just the economy of scale. So a lot of times it's relatively expensive to install all those sensors and to maintain it. So is it easier for larger plants? Just because of the economy of scale? Or is it, but because we're such a large plant, sometimes as you'll hear that there's other complexity that kind of makes it difficult to achieve a full benefit of it, especially when it comes to aeration control. But the nice thing about our, even though it's a very stringent permit limit, because it's a it's based on the mass load for the entire calendar year. It gives us kind of a lot of freedom to play around with the control. So even if we have like 1 month where we have slightly lousy treatment, we could operate kind of more aggressively the following months to be able to catch up. So because of this flexibility, kind of when we first started working on the control system about 5-6 years ago, my supervisor just gave me a lot of freedom to kind of play with it because, yeah, a couple days of bad treatment, we could always catch up, or not ideal treatment. And finally, for these stringent limits, maybe the question for everybody is, like, is this a driver or a deterrent to implementing complex control? Because like, if you're always trying to maintain this ultra low number, do we want to take the risk and trying to use control systems, or you want something that's simple and that's kind of foolproof? And I guess it all depends. In our particular case, definitely for meeting the nitrate, we definitely want the control system has been very, very helpful. We spend right now about close to $8 million a year in methanol. So just to be able to reliably meet the nitrate number without overdosing on methanol is a huge driver for us. But at the same time, trying to hit non-detect on ammonia, it gives us a lot of challenges. And today I'll mostly be talking about the ammonia aeration control and why it's been difficult to fully achieve the full benefit. Okay. And just a quick overview. So we have a traditional night-D-night system, activated sludge system to meet our nitrogen removal. But the one interesting thing is that's probably a little bit different from a lot of the plants out there is that all the carbon has been removed. So we have a chemically enhanced primary treatment using ferrochloride and anionic polymer, and additionally the high rate secondary treatment. So because there's no carbon, we're able to really maintain long SRT. And so after the nitrification reactors, we do have NOx probes. That's before the supplemental carbon feed is added and after, to be able to control this carbon feed. And it's been working really well. And then within the nitrification reactors, we have implemented some controls, and I'll be mostly focusing on the aeration control. Okay, so this is what our aeration reactor looks like, where we're trying to achieve that non-detect ammonia. As you can see, the influent gets fed in 2 different zones, and the flow kind of serpentines through. And there's a lot of DO probes all located all throughout because the individual zones are controlled separately, independently for DO. And then here we have a ion selective electrode ammonia probe and a UV-based NOx probe. And finally, before the supplemental carbon's added, we shut off the air to be able to try to knock down any residual DO. And we have some nutrient sensors. So this is 1 out of the 12 reactors that we have. So we have a lot of sensors. And Live's previous survey about which plant has more than 20 DO probes, yep, ours is definitely one of them. And especially the DO probes and NOx probes have been relatively reliable, but the ammonia probes are a huge pain. And just it takes a full buy-in from a strong INC group to be able to stay on top of it. And not just these sensors, but also in order to make the successful control work, you have to really stay on top of all your actuators, the different airflow meters, hardware, software of your controllers. Those all have to work really well. And I'm hoping some of our INC guys that are out there maintaining it are on this call, because I just want to give them a shout out that I really appreciate their work. And because we have such a good, strong INC group, we're able to implement a lot of these complex controls. And originally, we used to have all 12 reactors used to be heavily instrumented, but because of different process updates, we decided to actually get rid of a lot of the sensors and only have 4 out of the 12 reactors that's heavily instrumented, and really try to focus our efforts and getting reliability on those 4 reactors. And just because of the shortness of time, I just want to quickly also talk about the balancing the work order priority, because a lot of our maintenance groups are stretched thin. They just have to take care of the rest of the plant. So this is only a small portion of it. And a lot of times their main focus is going to be on permit sensitive or something that's related to throughput. So that's where all their priority is going to be. So say if like ammonia probe is out of calibration, they can't necessarily get to it right away because there's other more pending issues. So just a couple of the sensor maintenance and any kind of INC maintaining is tough. So originally we had the basic DO control mode, where you have your target DO set point, and there's a PID. It's actually more of just a proportional integral controller that sets the target airflow. And based on the target airflow and the measured process airflow, there's another PID loop that sets up the air valve position. So this is all the odd side reactors. Each one of these control valves have a fully independent DO loop. And overall, DO loop controllers does work well in meeting our process target, but because we have the flexibility in our control system and the ammonia probes, we also decided to implement this ammonia-based aeration control, where you have this high-level ammonia controller that actually sets the set point DO for stages 1 and 3. So just this set point gets implemented, gets put into this set point for DO. So it's a dynamic DO set point, and it's a triple cascade. And originally we had just a traditional PID controller for this. And in our particular case, I didn't get very good result out of it. And one of the main problems with it is that the PID loops, in our experience, has been just too slow to react. So by the time, we've a lot of times found our controllers kind of chasing after each other. And so that's why we decided we worked with a DCU provider to implement this a little bit more advanced controller called a Model Predictive Control, MPC. And what it does is, in addition to the effluent ammonia and your desired target ammonia set point, you also put in this what is called the plant flow. And that's what controls the set point for DO. And there are a lot of different types of MPC out there, but the particular one that we have it's a strictly empirical controller. So the way you tune it is on a given day. First, you set like your DO constant, and you monitor how the effluent ammonia changes as the plant flow changes. So that's one of the tuning parameters. And on the following day, what you do is you try to find a time when the plant flow is constant, and you make step changes to the DO and see how the ammonia reacts. So based on those two kind of like empirical real-time data, the controller gets updated and gets tuned. So a little bit different from your typical PID loop. And the MPC controller, once we got it implemented, it actually worked pretty well. We've been happy with the controller. So as you could see, once we turn it on, we're able to meet our target. And this is a very ambitious target. But the one thing that I do want to clarify is before the MPC is turned on, you see some of these big spikes on the effluent ammonia. And a lot of these spikes are kind of exaggerated because our ammonia probes are kind of the ISC probes are calibrated to measure very low level. that whenever there is ammonia breakthrough, it reads way higher than it should. And the one good analogy that I heard from the provider is that you're basically kind of, in a way, analogy would be like you're tuning your like a hearing aid to be able to pick up the very faint sound. But then, so you're able to distinguish just a small amount of sound. Then all of a sudden, somebody comes in and yells at you. And it's hard to get this kind of accurate feedback on exactly how loud that thing at you is. So definitely there's some major limitation on what you could do with the ISC probes. Okay, but overall, we're happy with the MPC when everything is working well, but that's the big but. One thing that I didn't show before is this, with this one control valve, it actually controls, so this is the control valve for stage 1A. It feeds the air to all the 6 reactors on the odd side. So like this. And these airflows are not on a control system. It's just a manual butterfly valve and a display of the airflow. So somebody has to go out there and manually set the butterfly valve to be able to get a good split. But the problem is, as this control air valve goes up and down to meet various airflow set point, it's always hard to get a good air split on the full wide range. So that's why even if the controller is working really well on the particular reactor that we're using to set the airflow, there could still be ammonia breakthrough on the other reactors just because of that flow split. And what makes it even more complicated is because of just the lag in the fine bubble diffusers. Each one of these 12 reactors are pretty big. So at most, we could do the full maintenance on the fine bubble diffusers, 1 or 2 reactors per year. So each reactor has a very different state on the health of the fine bubble diffusers, which makes it even more difficult to get a good split of the air. And finally, for the sensor maintenance, we have implemented a lot of the preventive maintenance program to be able to really stay on top of it. But at the same time, like our INC staff they have to maintain an incredible number of equipment out there. And so if there's other more process critical equipment that pulls them away, then what we're going to do is that kind of maintaining these sensors gets kind of put on the back burner. It just becomes easier to just put them in manual and just have a constant control and kind of forget about the more advanced control, because we could get away with it for this particular process areas. But for other process areas, such as thermal hydrolysis, you cannot get away with any kind of faulty sensor or control equipment. So those would take a priority. And so another major system limitation that we have is that we have these 2 massive blowers. So there are 2 4,000 horsepower blowers. And it's actually the air demand for nitrification system is only about half, 40 to 60% of the blower output. And good chunk of about half the air goes to the miscellaneous, the big other, which is like the post-anoxic aeration, a lot of the channel mixing, and to be able to maintain that final effluent aeration. So in a way, no matter how much we try to optimize the air demand and the nitrification, actually we've gotten a much bigger bang for a buck by just avoiding air wastage on other places. And also another kind of inherent system inefficiency that we have is these nitrification reactors are about 30 feet deep, and the rest of it is about 10 to 20 feet deep. So we have to kind of have a very high pressure to be able to add air to the night reactors, which kind of makes it a little bit more inefficient when looking at the system as a whole. And another challenge that we have is that this is kind of a busy graph, but this is looking at the blower efficiency since 2012. And on the purple, what you see is the air temperature. So you see it going down in the time and going up in the summer. And yeah, these blowers tend to be way more efficient during the colder weather and less efficient during the summer. But what's hidden in this trend is that not all summers we get the same efficiency. And it's interesting to see that this particular summer, we were getting the poorest efficiency. And when you measure it as like amount of power required to deliver a certain amount of airflow. And the reason for that is actually, so this summer where it shows, it seems like we have the poorest efficiency, also happens to be the summer where we have required the least amount of air compared to the previous years, and also accordingly have used the least amount of power in the blowers. But the problem is, like with these old school blowers, the centrifugal blowers that's not on a VFD, is you try to turn down the blower as much as possible, you basically get a point of diminishing return. You pay a penalty and less efficiency just because the base load on the blowers is so high. So you can only do so much turn down. And of course, maybe other plants that have a turbo blower, you wouldn't see this kind of severe split, and you might be able to get much better benefit. And just finally, I might be going over my time limit, but no matter how robust your control system is, you're always going to need somebody to be watching out on it. Even though we've been mostly talking about nitrification aeration controller, this is on our methanol control using nitrate probes. So if you don't stay on top of the cleaning, the probes, after a while, you're just going to start getting these crazy numbers. And you see that once the probes are clean, then the numbers, the readings stabilize. And just one thing, that just a practical challenge that we have is that if you're just looking at this trend, I think it's very apparent that the probe is fouled or there's some kind of problem because it doesn't make sense. But for our operators, this is just one of the thousands of different process variables that they need to be staying on top of. So just because this one went bad, it's difficult to catch it right away. And also another thing is it's kind of a, just a little dichotomy that we have is like the more robust your control system is and less problematic it is, then typically that means as operators, we would pay less attention to it. So when there is a problem, sometimes it's hard to jump on it right away. So anyways, this is the overall conclusion is that there's different drivers for automation. And more than anything, it's very important to get buy-in from the staff to maintain and keep up with the system. And then there's always going to be different physical and system constraints that prevent us from that could prevent us from obtaining the full benefit. And we always have to rely on good operators to watch over the system. So with that, I'll be happy to take any questions, and I'm looking forward to some good discussions with the group.
Thanks, Rio. That was a great presentation, ranging from politics over sensors to operator training, equipment issues, and controller issues. Very interesting. So a clear indication that there's quite a way for us to go before we can claim that we are able to properly run these systems at all times. So we have questions coming in. First question from Ali Gagnon from HRSD. Very good question. The MPC have to be recalibrated periodically, and specifically, have you noticed any impact on the MPC after recalibrating the ISE probes? Very good question. Rio, can you answer that?
Yeah, that is a great question. So I guess maybe I'll answer the second part. In general, yeah, the MPC would only really work when the ammonia probe is fully calibrated. So that's one of the main assumptions, and it wouldn't help us out that much if the ISC does drift and we lose calibration. So it's not a matter of having to retune the MPC. It's just making sure that you're able to stay on top of the ISC probe. And another thing that we haven't really looked into is, I guess, imagine the MPC would need to be retuned based on different seasons or mixed liquor concentration, various factors. But to be honest, we haven't really fully looked into it yet to kind of measure, fully quantify the performance of the MPC in various conditions.
Yeah. So we got too many questions, not enough time. So we will ask Rio to answer all your questions in an email afterwards.
Oh boy!
So I'm.
I didn't sign up for
Yes,
that.
I didn't tell you that, but that's in the fine print. Anna Pena from Fort Worth is asking why the blowers were more efficient in 2016.
In 2016? Oh man, I'm glad you asked that. It's because that was the time when we're actually using more air. So remember these blowers, just the apparent efficiency, how much power the blower is sucking per airflow. The more you push the blowers, you get better efficiency.
Okay, so that's the efficiency curve of the blowers, and that's the air consumption was more favorable for the curves.
Yep, exactly.
Good. So I jump over the MPC question, so that is probably too long, but maybe you can answer, does the auto cleaning probe also need to clean?
Yes. There's certain type of auto cleaning that's a little bit more efficient, but yeah, effective. But in general, yeah, we have a PM where our techs go out and periodically clean the DO probes, ammonia and nitrate, and that is very critical.
Okay.
So yeah, the auto cleaning alone hasn't really solved our problem.
Right. Yeah. Maybe one on operators again from Anna. How do operators prioritize activities? So you mentioned that they decide, but I guess the question is, how are these priorities set? Is that done from you or by you, or is that something the operators decide on their own?
Usually, at the end of the day, for both O and M priority, it's the biggest thing is the critical equipment availability. Mm-hmm. So we have to have so many numbers of equipment fully available to meet our permit. So that's what drives it more than anything.
But you have clear rules on priorities. I think that's the question.
Yeah. So what we have is the minimum number of equipment required per area.
Okay, very good. So that fits into resilience management, I guess.
Yeah.
Good. Unfortunately, we have to close that now. So otherwise, we don't have enough time for the other speakers. Thank you very much, Rio. And again, we will get you an answer on your questions. So we will collect them and then send that to Rio and hopefully get responses from him.
Yeah.
Thanks a lot, Rio. Great presentation
thank you.
Great information on challenges utility phases.
Yeah, and I just realized I had my camera off. I know you wanted it on during that presentation, but
yeah. Well,
all right. Thanks for the questions, and let me present our work here.
Okay, thanks. Good, Manel. The next Mentimeter. So we are now moving into the next session on analysis and design. Yep. Okay. Okay. So I think you jumped over Oliver's questions. Yeah. Good. Okay. The question is, how is the overall performance of your aeration system? So we just want to get a feedback from you if you are satisfied with your current system, or the system you last worked on, or if that is quite challenging. Oh, yeah, it looks like there are plenty of challenges out there. Okay. Yeah, well, more or less satisfied is catching up. Okay, so the fastest ones were the people quite annoyed with the performance of their control systems, I think. Good, let's wait a little bit longer. Okay, so I would say there is a trend, a clear trend that these systems are quite challenging, meaning that people are not really satisfied with the performance, right? So clearly an indication for me that there's work to do. Okay, Manel, next question. So if you have a better understanding of your aeration control system, what is your opinion? What is limiting that performance, right? So is that sensors? Yep. The first ones are just clicking on sensors. Is that maybe diffuser distribution, valves and pipes, blowers, the control system itself? So that would include the control logic, or how the system is set up, tuned, and so on. And then the last one is operator training, that these systems are so overly complex that nobody can actually run them properly. Okay, right now I would say sensors are in the lead. Blowers is something people are quite comfortable with, it looks like. Our experience is actually different, that blower control is quite challenging. Okay, control system. Yeah, so it sounds like the control system itself is also something where people think could be improved, and is limiting performance, right? So the idea here is to get a better idea of what you think is causing problems. Is that sensors, equipment, the process itself? If the process is not properly designed, then that could also cause something. And then, of course, the control itself, and then we added the operator training, so that we have some soft skills or non-technical issues here as well. It looks like the control system itself is seen as the main issue here. Yeah, next question. Oh no, that was the two. Okay. With that, I hand over to our CTO, Oliver WRRF, in front of the beach. So you see we have plenty of fun and a nice work environment in these days. Oliver.
Okay, can you see my slides right now?
Yes.
Okay, great. Okay, well, welcome everybody to the webinar, and thanks again for attending. And thanks to Rio for a really nice presentation that really set the stage for a lot of the, identifying a lot of the practical issues that you can experience at the plants. So I'm going to now get into identifying some of the process equipment and control limitations in aeration systems using process models, and going to give you an introduction to it, but then the heart of the presentation will be getting into a few case studies that we've done over the last few years and kind of highlighting some of the things we were able to find using sort of an integrated model of the entire plant and its aeration system. So start out, I'll give you an outline of the presentation. I'm basically going to kind of talk about the current approach that's been, done in the past and is still typically done for designing aeration systems. Talk about a new integrated approach, sort of using an integrated model of the whole system. I'll kind of explain some of the insights that we typically find using this approach. But then I'm going to sort of highlight those by getting into some real case studies that we've done, and then finally I'll have summary and conclusions. So in terms of the current approach to aeration system modeling, and as part of sort of the aeration system design process, basically simulators in the past have typically focused on modeling the oxygen transfer. And this is, quite well captured in the simulators. And basically, you for the most part, you'll specify a DO concentration, and you may have a controller in the model or not. But in any case, essentially, the model sort of back calculates what airflows would have been required to allow you to meet those dissolved oxygen concentrations. But basically, the supplied side of air supply is not really modeled in detail. So typically, it's assumed that the aeration system can, supply whatever demand you have. And you typically aren't modeling, the air distribution system with the pipes, and you're not really modeling the blower characteristics in a lot of detail. And if there are any, system constraints, they're typically handled with simple bounds. Now, basically, to get into the motivation why we thought a new approach was required, basically, I think if you do it the way I mentioned on the previous slide, the simulators can definitely help you determine where and when you're going to need to deliver air to meet your treatment objectives, which is quite useful and will help you find the best DO set points and determine, the maximum and minimum air demands. But the problem with that is they don't necessarily then give you any insights into the behavior of the air supply system. And so, basically you may find that, the models in this case would indicate that you can meet these DO set points. But in reality, you might find in a real system like Rio's that, maybe these DOs may vary more than you thought they would, just because you're potentially hitting some constraints. So, some things you might want to look at with this kind of, but you can't really look at it is with this approach is that, am I really going to be able to meet the maximum demand at high air temperature? Because that's when I really am going to be taxing my blowers, the most. And is my control system going to be really stable? You may have some issues that you hit, but you don't really know a lot of times until you've actually commissioned the system and put it into operation. And, what are the different energy cost implications of different control strategies? So that's sort of why, well, actually, to get into it a little bit more before I explain why we decided to go a different route, I just wanted to explain that, as part of typically designing aeration systems, typically this is done by separate groups. So we'll have, process engineers using design standards and steady state models to design the plant. Typically, they might use simulators to fine-tune the design, determine the air requirements and optimize the operating strategies. But then they'll kind of pass things over to mechanical engineers who then, use separate software to, specify the blower design and the aeration piping. And, typically these will be in separate reports. And then there might be then, a report and commissioning plan from the control engineers, and they may, probably use separate software to sort of design and control and tune the control system. And then, you essentially have this work done by 3 different groups typically, and then, at the time of commissioning is when you have to work out all the little issues that may come up because of the fact that these things were kind of designed and looked at separately. So that's kind of why we felt that it was time to, if you're going to use modeling as part of this aeration design process, why not use a model of the entire system so you can account for the interactions between the different components in the system. So this little animation here is basically showing a Simba model where you have a fairly simple air supply system with a blower, and piping and valves and diffusers, but basically it allows us to kind of, even in this simple system, get a feel for the complex interactions that are occurring. And basically when you add control to one of these, a plant, basically you suddenly have created interaction between the air supply and the air demand. If you didn't have control and you were just supplying air, the only interaction would be you to, watch what happens and then potentially decide to make a change manually. But, there really isn't any real interaction. But once you put the controls in place, you've essentially created interaction and you've created feedback. And that's when you really need to, pay attention to the dynamics. So a few things I wanted to get into with some of the equipment that you experience with aeration systems, or that you have with aeration systems, sorry, and some of the things that that we've sort of observed using this approach with an integrated model, and then I'll kind of get into some actual case studies. So first, talking about blowers, as I'm sure everyone's aware, they're typically the most expensive equipment at a plant in terms of actual, equipment, not concrete, but in this case, just a working piece of equipment. And they're typically the biggest energy consumer at the plants. Now, in terms of sizing blowers, you really need to take into account the air demands of the system, and how they change over time. You need to be aware of essentially the aeration system curve and how that changes and varies under different operating conditions. And you basically need to know the blower curves as well, because all those three things kind of interact. The actual performance of the system, how much air you actually will need, and what the blower can supply. And the issue with this is it's one of the most important things, of course, because if you don't have enough blower capacity, then potentially you have a process failure, or you may exceed your permit. If you have too much capacity, then typically you're always going to be running at a reduced efficiency, and you may not be able to turn it down as much as you would like. So when you do classic engineering design, typically, as I mentioned earlier, you're going to design these systems separately, the demand and the supply, and a lot of times the work's done at steady state, and then typically with that, it becomes difficult to really see the impact of any potential limitations in the equipment. And you may miss certain plant specifics that typically would lead to higher, for example, pressure drops than you might encounter with a spreadsheet design. Because with the spreadsheet design, you can't really account for all the possible combinations of valve positions that may occur at any given time. So, in a big plant, you could literally have, a huge amount of different valves all operating at the same time. And it would be very difficult with a steady state spreadsheet approach, to figure out, what's the impact of all these different combinations and how would that affect, the system pressure. So the approach we've been using with this integrated model, where we integrate the process, aeration system, and controls all together in the same model, it allows for a holistic analysis, and this allows for more tailored blower designs. And one of the big things with this is that you can model things that are typically hard to measure, because you may not have sensors everywhere, and if you have a model of the system, you can essentially model things that are hard to measure. And the other thing is with this approach is that you can test the designs in a realistic simulation to really reduce risk when you go to commissioning. Because if you model it as realistically as possible, then, the controller tuning that you develop in the model is going to be a really good starting place for the tuning in the plant. You'll always have to fine tune, of course, but you'll have a really good starting point. And that's one of the hard things, when you commission these systems. Now, in terms of the piping network, obviously the construction of the piping network can be expensive. And one thing that's usually, has been done in the past is that, fairly cheap butterfly valves are used because they really, are a lot cheaper than some of the newer valves that are out there. But they, provide somewhat limited controllability of the airflow, and the positioning accuracy isn't as good. So there's, newer valves now that are much more precise and have much lower pressure drop, but they can be more expensive. So it's something that you have to sort of keep in, make a decision on whether, the added expense is worth the extra, improvement in control performance. Now, typically, if you're sizing, pipes and valves, it's going to be based on looking at velocities in the pipe and your, estimated airflow ranges. And the thing that can be an issue, of course, is that these pipes potentially could be bottlenecks and may require a higher system pressure than you thought if you didn't really look at how the system would behave, once the controls were in place. And the one, common problems, of course, that you can have is if your valves are too large, you can't really have very precise control of your airflows. But if they're too small, you may have too high of a sort of a pressure drop, and essentially you might be causing a bottleneck for your air supply. So typically, with classic engineering design, you might use separate software to design the piping or do it with spreadsheet. But typically it's done at steady state. And again, then the focus is purely on the air supply itself, not on the demand in this case. So our approach has been to try and dynamically integrate, the process, the aeration system, and the controls. And sort of, by doing that, we can match the piping design to the varying air demands and system constraints. And again, the model allows us to measure things or sort of, predict things that we can't easily measure. And, one thing that we typically find is that it helps us identify, bottlenecks in the piping network. So that sort of sets the stage. I wanted to now get into, some actual case studies where we've used this approach and give you some of the, highlights of what we found. So the first one, it's for the Los Angeles County Sanitation District, the San Jose Creek East Water Reclamation Plant. It's a 62.5 MGD design flow plant. It's basically 5 parallel trains, and each one is a 4-pass step feed basin. Now, the scope of the work was basically to support them during an upgrade of their aeration system. And in phase 1, it was more looking at the process side, and we wanted to identify the cause of ammonia breakthroughs that they had periodically, throughout any given day. And we wanted to compare step feed, the step feed they're currently doing versus an MLE configuration. In the next phase, we then looked more at the aeration system, and we wanted to provide a design basis for the blower upgrades. But as part of that, look at any piping bottlenecks, and we wanted to evaluate blower control strategies that employed a most open valve strategy. And we also wanted to provide system curves that their design department could be used for their blower design. Now, some of the highlights, basically, we found actually that the ammonia breakthroughs were more caused by uneven flow splits as opposed to, any inhibition of nitrification. But one thing we found with looking at the aeration system was that when we went to this blower control strategy where we had a total airflow-based blower control, and we had DO control in all the aerated grids, which they didn't currently have, but they wanted to look at if they had, DO control in all the grids. we found that actually the overall pressure drop increased, and that they had to go to a blower with a higher discharge pressure than the blowers they currently had. So that was actually quite important thing that came out of the work. The other part we found too, that part of that was that we looked at where the high air velocities were, and in this case, the big ones were really in these what they call neck down sections, where basically they had these an original system where the plant was built in 1969, and you have sort of existing holes through the walls between passes, and they wanted to basically they reused these holes to put some new piping through when they upgraded over the years, and so they had to kind of neck down and go to a smaller diameter to fit through these existing holes, and then expand back out again when they connect with the drop leg. So basically, the pipes that connect to the basin headers and then supply air to the drop legs, those pipes had to shrink down in size, and there's fairly high air velocities when that happened. And so that's actually something now that they're definitely going to be working on as part of the upgrade, is to try and increase the size of those pipes so they don't have those bottlenecks. Now this actually work is going to be presented at Weftec next week. We have a presentation, a video presentation that you'll be able to watch if you register for the conference. The next project is we did for the city of Fort Worth. It's the Village Creek Water Reclamation Facility. And we actually, I think we have Anna from the Fort Worth on the call today, which is great. And basically, this plant, the design flow is 166 MGD, and basically they have sort of three kind of sections of the plant. In a sense, almost three activated sludge plants in parallel. So in the first section, got 6 completely mixed basins, and each one has a pre-anoxing zone. In the next section, we basically have 3 basins, plug flow basins, and they have 4 passes each. And then finally, we have 4 one-pass plug flow basins. And we had a number of phases to this work. The first phase was to troubleshoot the aeration control system. The next phase was to do a blower risk assessment. And then finally, in the more recent phase, well, we've been doing a number of things, including training, but one of them is also studying some air leaks in the system. Now, some of the highlights, in phase 1, we did identify some control logic issues, and we recommended, a solution to kind of address those issues. We basically, looked at the performance of the system, and we were able to kind of determine, the way the controller was performing, and came up with a sort of a strategy to improve that. And we also, found that there was some airflow bounds that were imposed in the SCADA system that were, limiting air to certain parts of the plant. In the next phase, we basically not only modeled the the process side, we modeled the entire plant, including the aeration. And as part of that, we definitely found that in the future it would be good for them to have some additional blower redundancy, because at the moment, during really high loads and high air temperatures, there potentially would be using almost all their blower capacity. So that was something interesting to find, and as part of that, we also found some piping bottlenecks that made it somewhat difficult to control the DO in certain certain passes of certain basins at certain times during the day. So we sort of identified some bottlenecks that are causing some issues. Now this is actually being presented at Weftec next week as well, so you can look for that if you've registered for the conference.
Oliver, can you move a bit faster that we have some time left for questions?
Yeah, okay, I'll have to speed up a little bit here. This one is the Toronto Ashbridges Bay treatment plant in Canada here. It's basically 11 parallel trains and a 4-pass step feed layout. But part of the work is they want to add a couple of new trains in the future. Basically here, we wanted to provide sort of design inputs for the aeration system upgrade, looking at operational ranges for the blowers, any bottlenecks in the piping network, and looking at the diffuser distribution. And they also wanted us to spend a fair amount of time looking at the control strategies that they were thinking of going with and how well they would work. The big thing we found here is that, we found that we came up with some, optimization of the diffuser distribution, which allowed the system to be, better tailored to the step feed splits that they would like to use. In terms of the control system, we basically went with as simple as approach as possible because it's a big plant, and they didn't want too many, a huge amount of sensors. So we went with one DO sensor per pass, and we looked at a few different blower control strategies, but it seemed like the pressure-based approach with the MOV strategy worked the best. And, as part of this, we provided a design basis for the new blowers. So they kind of had an operating window in which we gave them where they know now that their blowers have to be able to work within that window. I don't know if I have time to go through all these, but this one was another step feed plant, but it was more of a greenfield site. Basically, on this one, we again found that there was some improvement that we could make where we could better tailor the diffuser distribution to the step feed splits. We found that's a common issue with these step feed plants. We did also find that there were some issues with the ammonia feed forward control logic, and we made some suggestions on how to address that. And we addressed some of the different control strategies that they were thinking of exploring, and found that really a simpler approach was better than some of the more complex ideas. And as part of this too, we did definitely identify some pipe and valve bottlenecks and that need to be addressed. So that we were able to actually find a lot of potential issues with this system. And this is kind of in the design stage, before it's even been built. This one is basically we did a project at a plant where it was a training model. They were getting a new control system, and they wanted to have an operator training simulator to kind of show them how that control system would work. But we basically found that if they simplified some of those strategies, they could significantly lower the number of sensors and maintenance required, and it would still work pretty well. And we found that the strategy we recommended with ammonia-based aeration control could save about 20% in energy. But actually, what was really interesting was we found that if we changed the diffuser distribution, we could actually save them another 14% DO control, and even another additional 7% for AVAC. And the other thing we found too is that they weren't necessarily operating all their bioreactors, but we found actually that things would be overall performance would be better if they operated all of them. Now the final one is the Chicago Stickney plant. This one, as I'm sure a lot of you are familiar with, is quite a large plant, and this study was actually done by one of our clients who used Simba to do it. But we, helped them put the aeration model side of the overall model together, and they basically found that at this plant, if improvements were made to the aeration control, they could lower the energy demand by about 30%. But it was really essential for them to improve the blower controls to allow this to happen. And, you know, they found a number of bottlenecks in the piping system, and they were going to analyze those in, you know, more detail in the next project that they were doing. And this works in a paper from Weftec 2015. Now, basically, just to summarize and conclude the presentation, we've been trying to show that if you do integrated modeling of air supply and demand, you can really analyze the system as a whole. So you can do holistic design. You can basically reduce risk because you can, you know, test the system in a lot of detail before you actually do the commissioning and after the commissioning as well. And you can really identify potentially causes of control problems, because you want to find out, is it the controllers or is it the air supply bottlenecks that are causing you trouble? And another, you know, big use of it is to, you know, evaluate plant upgrades, new equipment, and control strategies, you know, before you actually implement them. And you can really make realistic comparisons of new equipment and, you know, different aeration control strategies. So that concludes my presentation, and thanks very much. And I don't know if we have time, but if there's any questions right now, I can try and answer them.
Yeah, please put your questions into the chat window, and then I will read them, and I'm sure Oliver can answer all of them. Okay, first question comes in. After all these recommendations, does the planned operation go great in energy saving? If not, what's the reason?
Yeah, basically, I mean, obviously, as you can imagine, it depends site by site. It is, you know, a lot of these cases, these studies were identifying issues, and then of course it takes time to you know, for them to actually be implemented and take effect. So if, for example, in the case of Los Angeles, you know, this is still an ongoing process where they've now you know, essentially put the you know, the request out to get bids on the blowers, and they've been working on, you know, planning out some of the upgrades to the piping, but they haven't actually done it yet, because as you can imagine, that construction work, you know, can take a fair amount of time. So I would say that you know, in cases, for example, where we've looked at it at the control side itself, and we've made, you know, suggested improvements in control strategies, you know, when those are implemented, typically you'll see those results pretty quickly. But you know, if it's something to do with equipment limitations, of course, those take time, you know, to get implemented. And those usually are going to, you know, show up as now you don't have a limitation, whereas before you did. So in turn, you know, that may or may not, you know, save you energy. It just depends on what your objectives were, whether it was just to save energy or whether it was to improve control. So I guess you know, basically it depends on each study. You know, some of them, if it was more control, you'd see the improvements right away. You know, others, it just takes time because there's a lot of construction work that's, you know, has to be done.
I'm sure there are more questions, so we still have time for a couple. For me personally, the most amazing aspect of these models, these integrated models, is that at times, and quite often actually, it goes against your common understanding of these systems. Right? So you really have a way to look into details where you don't have measurements. So you basically guess as an engineer after a couple years in the industry, you think you understand the system, but actually I learned a lot. So more recent, we had one case where DO is typically something where you say, oh, the lower the DO, the more energy savings you should see, right? And then if you go a step further, you say, well, if we reduce the airflows, then we should see energy savings, right? So what we had in one case was that there were valves closed, and pretty much completely closed. And the pressure drop these closed valves triggered were so high that yes, the DO was reduced, yes, the airflow went down, but the pressure drop was so high that you actually had to run the whole system with a much higher pressure. All right, so that's a combination of the controls. You have a lot of feedback loops, and in the end, they consume more energy. Quite interesting, right? So you reduce the DO and the airflow, and still the energy goes up, right? So quite interesting. No questions?
I was just going to
You're
add.
tired already.
I was just going to add on that last one that the one challenging thing, of course, with looking at energy, cost comparisons is establishing the baseline. And there's another case study we have, which we didn't actually show here, but where ABEC was done. But on that, what we find is it's a bit somewhat complicated to figure out and work, with the plant to figure out what's the appropriate baseline that you're going to compare against. And that's, I'd say that's actually one of the more trickier things in terms of once you implement these kind of improvements to see how much energy or does it save. It really, to really get a good picture of it, you have to really have a good baseline to compare to.
Okay, so there's another question. Except for the aeration control, does your company do carbon dosing control and other controls?
Yes, we do. We do, look at all different types of controls at wastewater treatment plants. As far as dosing controls, I can pass that one over to Live. He has actually did look into that, where we had a model, sort of a model-based methanol controller.
Yeah, so methanol control is quite tricky because you have to grow and maintain methylotrophs, so a special type of organism, and that adds to the control challenge. And I think we found quite an interesting solution to do that. There's also a paper on the Weftec paper on that I can send you. Other controls, we looked into classic feed forward control for dosing chemicals for phosphorus removal. We had one very interesting project on dewatering, so polymer addition or dosage for sludge dewatering. I hope that this is, so we did the pre-study proof of concept. That is basically a data-driven model with a controller and optimizer on top. And the results were very impressive. So the tricky bit is that that process is not well understood, I would say. So data-driven models are much better suited. Right now, we are working quite heavily on phosphate or phosphorus removal control, basically a controller to control BioP, right? So to my knowledge, there's not a lot out there right now. And we also have quite some promising results right now. So that's an ongoing research project right now, but I'm sure that within a few months we have something there. We do evaluation of controls. We help with implementation or designing controls, so tailored controls. So quite a range. Yeah. So next question is that side stream EBPR as well. I would say the jury is still out on side stream EBPR versus mainstream. Basically, the important fact with BioP control is that you have to be able to predict with a time horizon. I would say you need probably at least a day, right? So because if you see that something doesn't work, the problem typically occurred a day before. Yeah, so that's the tricky bit we are working on. right now to have a data-driven predicting these upsets. We are not quite there yet at a full day ahead, but we are getting closer by the day. Yeah. So, and then it doesn't matter if it's side stream or mainstream. We use data-driven models, and the models are in real time impressive, right? So me as a mechanistic modeler, I would say I'm very impressed. And we have very good prediction results with a time horizon of 6 hours already, and we are continuing to improve that model. Now we are integrating additional measurements. Good. With that, I would like to move on so that we are having enough time for the last session. Again, we start with the Mentimeter survey. So the last session is about some of our solutions. And Manel, can you go to the next slide? Manel, can you move to the next one? Something does not work. A little slip. Okay, Manel, do you fix that or should we move ahead? Okay. Okay. Oops. I didn't even read the question. Already 6 people answered, so that is predictive answering, I would say. So the question is, how do you monitor the quality of your controllers? So we have a couple of answers here. First one is basically we don't. We only look at the effluent. The next one is we compare set point and measured and decide if that is close enough. Then we regularly check. So that means a full analysis of set point versus controlled variables, or what you measure, but also looking into the manipulated variables of the controller outputs and all the constraints from equipment and process, which in the controller itself will be covered by the bounds. Yeah? And then the last one is we have an online performance monitoring system in place. I would be quite interested to know what type of system you're running. Maybe you can disclose that at the end of the presentation. Good. Manel, I think you jumped over one question. Okay, no, very good. So the next question is, how do you monitor the quality of your measurements? Quite important, of course, that you have correct measurements entering your control system. The first answer, that is something I get very often. If the plant has a sensor, but it's not really used, then it's forget it. We are only looking at trends, right? If it's going up and down. Then the next level, I would say, is we measure if something looks not quite right. So that is already an improvement, I would say, because that means somebody is looking. If the data makes sense, it means that the data is visualized and somebody is looking, right? So that is the probably the most important first step. And then we go into more strategic ways of making sure you have proper measurements. One is that you have a weekly reference measurement taking, analyzed in the lab, and then you compare lab and analyzer. And then the last one is that you have an online fault detection software. So the weekly means at least you have one data point a week. In our opinion, you should go a step further and make sure that we have something in place where every single value entering your control system is somehow checked. Yeah. And quite interesting, 10 people responded and not one has an online fault detection software in place. I hope that Ivan can convince you that that actually is possible and makes sense. Thanks. With that, I hand over to Ivan.
Okay, thank you. Can you guys hear me properly? I hope that's good. I'm going to talk to you today. I'm going to show you a few slides about control performance monitoring, specifically geared towards process control. But I hope you get some additional ideas of how fault detection systems can work in general to your advantage, especially if you have a software framework behind it to support the algorithms. Okay. So the main focus of what I'm going to show you is going to be on fault detection with the application to controllers, but you're going to get some ideas for looking at sensor faults in an automated fashion, and also how to use soft sensors, that is predictive models, to make inferences of quantities that are difficult to measure, but also how you can use technologies to monitor a process itself for faults in real time. And I hope you get some ideas on how to put this all together and make it work in the real world. Okay. All right, so let's just start with performance monitoring methods in general. And this is a question about fault detection applications. When we're talking about fault detection, really what we're saying is that you're going to compare how current performance, it's going to be either of your process or of your controller or some piece of equipment that you're looking to assess, how that's performing relative to a benchmark. Okay, and typically a benchmark involves developing some kind of a model, or comparing to some standard measurements, or a theoretical kind of an assessment, and seeing how the equipment or the process is performing relative to that, and then coming up with a metric to evaluate that performance, and then plotting the metric or visualizing it, and then deciding what to do about that. And what I hope that you understand from this is that at least in my opinion, that algorithms and math and all of that, the technical piece is not really ever enough. You have to build something that's in a comprehensive kind of a system that gives you a useful interface and a display and an output of these methods, so you know what to do with them, with the models, after they give you an indication of what's happening. Okay, so this is just like a very brief reminder of one very popular approach of how to do fault detection. And what you're going to notice through if you're following these slides, is that they're basically an application of control charting methods to various scenarios, and integrating these control charting ideas into different workflows to give you this ability to track the performance of what you're looking for. So again, briefly, remember that a control chart is a very simple data model. It's a data model that specifies that your process has a fixed mean, and it has a fixed standard deviation. And then once you've established what those values are, you're going to plot your new values, your new data, on a chart, and you're going to see if any data points go outside of these limits. And if they do, you're going to infer that a problem has occurred. And then what you want to do is have some ability to diagnose the problem after the control chart has detected it. And these control charts can be used in various groups or with each other, or one control chart, many charts, and you can apply them to single variables or multivariable models, depending on what metric you use to put on your control chart. So just realize that what you're looking at moving forward is going to be applications of charting technology. Okay. And what we're talking about here is applying these methods for fault detection, again, univariate or multivariate, but still through control charts, to these three basic pieces of a feedback loop that's a part of pretty much any plant that you find that uses controllers. So you have the process, it's connected to sensors, and that feeds into the controller, and then there's a feedback through a control element back to the process. So we want to see if there's any faults or problems in any one of these, either the process or the sensor or the controller, or maybe simultaneously, if there's anything going on in any one of these. Excuse me, we want to be able to provide an indication that this problem has occurred, and to see if we can do something about that. All right. And then again, I guess that this is just repeating that same point that I made earlier, but I think this should be underlined, is that the algorithms and the math are not enough, at least not in my opinion. You need to be able to look at efficient ways to summarize these statistics and the outputs of these fault detection schemes. All right, so let's look at what this might look like for sensor data quality monitoring. Okay, and what you're looking at is an interface in or one of the interfaces that we have in our in a software that we're developing, our ops control software. The main point here is that although you're talking about assessing the performance of sensors, and you should realize that you're looking at potentially monitoring and putting together data sets from various channels, each sensor being able to provide you with more than just one measured quantity. And what you want to be able to do is put them together in real time or near real time as you get the values, and then assess them one at a time or together in some charting methodology that you might want to apply. Okay. And if you look at this then in the form of say one channel per or one of the sensor channels, in this case it's for I guess for temperature, for Animox effluent sensor, we could apply a control chart to see the difference between the laboratory and the sensor value as the laboratory and sensor values are coming in, so in real time or near real time. And someone in that survey was saying that they do this maybe on the frequency of one or two measurements per week. It could be done at that rate, or slower or faster. But when the data are available, what you want to do is to be able to process the data and put them together in one place, manage the data so that you can get a clear indication or an alarm regarding how your process or how your sensor is operating over time. Okay, so in this case, it's a Schuhart chart that does that. Okay, and you also have diagnostics that you would want to look at, for example, to see if you have enough data points, where the data points are being collected, at what sort of range or spread across the sensor measurement window, and how this can compare to the lab, and to see if there's anything deviating there regarding that might indicate that you would need to recalibrate your sensors or clean them, or give you an indication that the operation is degrading. Okay, so we can support that with calculation modules like this through this kind of an interface. Okay, so now control performance monitoring. So let's have a look at that. The main message with this is that the question of control tuning should be brought together with the idea of detecting any faults or any operational issues with a controller as you're monitoring the performance. So as all of you may know, that the idea of tuning a controller is kind of choosing these controller parameters, the KC, tau I, tau D, to, and in the case of a PID controller, to achieve a better ability to say track set points over time. And that's what you see here is in that top plot on the right hand side of the screen as you're looking at it. Before tuning, you see that the blue line is not able to track the red line very well. There's lots of variability there, and lots of offset and difference between the red and the blue. And when you look at the effect of tuning after you apply tuning, the controller, in this case it's a PI, is much better able to track the set point over time. Okay, and what we're showing here is an ability to apply an automated tuning algorithm that you can at a click of a button or completely automatically provide for you tuning parameters for your controllers at any point in time through automated performance assessment, or you can do it semi-manually. Okay. So how does this look in practice? The general idea here is that you would look to apply routine process data. So if you can, you would want to avoid wanting to put in step changes and these kinds of things into your process if you don't want to, or if you don't have to do that. But of course, if you do need to, we can support that with how the algorithm works and how it operates. But the idea would be to use existing routine process data to fit a simple plant model to the data that you have stored in your DCS or your databases, and that is to apply automated model fitting. And then we would use a tuning algorithm to develop a theoretical benchmark for what we consider a well-tuned PID controller, and then compare the current tuning that you have in your plant to that theoretical benchmark. And then we can advise through the operation of the algorithm how you might want to adjust the tuning of your PI controller or some other kind of controller that may be applied through automated tuning, so that you can get a better set point or disturbance rejection capability out of your controller. Okay, and this can be done in an automated fashion. All right, so another example of what you might kind of face with this, and this is sort of a practical thing that Live and I and our colleague Masa worked out together over the last little while, maybe the last few months. The idea that performance assessment is not really clearly defined if your controller or your processes is facing process constraints or equipment constraints. So what you would want to be able to do, and in this case it's for an ammonia controller, here we're not able to really assess the performance of the controller or give you an idea of how well it's performing because the diagnostics checks are indicating that there's a lack of information in the data because there's not enough variability in the set point, which indicates that you might want to put in some step changes to move this controller around to give you the information, but also that the manipulated variables have hit certain bounds. So we can assess then in real time the performance of the controller or the data that are coming into the controller and really see how well the system is operating based on the quality of the data relative to the expectations of the controller. Okay, and this is an example of how this might work for a DO controller. In this case, realize that the that we're analyzing this entire cascade, and we started with the ammonia controller, but here we're looking at the DO and the controller below it. So our approach to this is to evaluate the controllers that are further down into the cascade, and if their performance is reasonable, then we can evaluate say the current controllers. So in this case, we're evaluating the DO controller because the air controller there is actually performing well. And in this case, we have a running real-time metric of the controller performance, an index of its performance relative to a reasonably tuned good PID controller. And we can look at KPIs, various key process indicators on how they can how you can that can help you to diagnose what's happening with that performance index. If the index is too high, it might indicate that the controller is not tuned tightly enough, and that you might want to retune it. So why did that happen? Is that because of the model fitting that you've done? Is it something in the raw data that you're using to do the assessment? These kinds of things you can glean out of the key process indicators. Okay. In this case, this pressure controller is showing a warning, but if you notice below that, all of the input data into the algorithm, into the analysis, seem to be in good condition. The manipulated, controlled variables and the set point seem to be okay, and that allows the algorithm to process the data and then to provide new tuning suggestions for this controller. So then you can go through the software and look at the tuning suggestions that the algorithm provides. You can compare them to your current tuning settings and see whether the controller is a little bit more aggressive or a little less aggressive, depending on what the algorithm is advising you. And then you can adjust that tuning if you like manually. If you have expert knowledge, you can tweak relative to what the algorithm has given you. And then at a button push, we can send the controller tuning parameters down into the DCS from the software so that they can be applied in the controller, and then you can continue to monitor the performance of the controller over time after tuning. Okay, and then to support this, you get to see various plots. It's not, we didn't show all of them here, but you can look at how the performance is of the controller is with the current tuning, with the new suggested tuning, all against the simulated case using that fitted plant model. So you can do what if scenarios and adjust the tuning of the controller and see how your tuning choices or what the algorithm picked for you is going to, how that's going to look in terms of the performance of the control of the error term, for example, in the controller. Okay, or you can look at the MVs or the CVs, depending on what you're interested in. Okay, all right. So the other part of the loop, that feedback loop that you might want to think about monitoring is the process itself. Okay, and this is concerned with applications of, say, soft sensors. Okay, so in this case, realize that what we're talking about here is an application of mature technologies that are centered on the right-hand side of that plot, which are PCA and PLS multivariate statistical methods, and that have a really good track record, especially in chemical engineering, in acting or in being put into applications of, say, soft sensors and for process monitoring. And the key thing here is that when you apply these methods properly, you would get a built-in diagnostic that goes with the algorithm that can help you monitor the operation of the soft sensor and the process itself. Okay, and in terms of a PLS soft sensor, what that means is that we're able to monitor the input data that go into making the prediction, and we can assess them relative to the model and what the model expects how the data should behave, and then we can also assess the values themselves, sort of the outputs of the soft sensor. And this can be done in real time. So now, because the data are being assessed, the input data are being assessed by the soft sensor, it gives you a built-in monitor for process faults. So what that really boils down to is that we can summarize a multivariate soft sensor into 2 control charts. That's those 2 plots in the middle. And then you can use those charts to diagnose and debug, say, outliers or any data that may be walking away from the in-control, kind of a below the limit normal operation of the data. Okay, so you're looking at applications of 2 control charts in this case that summarize your process. All right. So again, back to this software interface. What we're looking at here is a soft sensor that predicts, I believe, 9 variables in this case, and you're looking at 3 of them. You get the instantaneous values across the top for predicted PO4 effluent, NOx, and ammonia effluent in this case. But you can also see a comparison between the process value and the soft sensor value on trends, and you can follow that and see in combination with performance metrics for the predictions how well the soft sensor is performing. Okay, now as this is operating, as the predictions are being made, you can look at the input data on those 2 control charts that I mentioned, and if the control charts are indicating that there may be a problem with the input data, you would get an indication that the predictions may be questionable. You would get color changes and indications, like visual indications, that you may want to be careful about using these values. And then you could look at the charts and look at the diagnostic plots that are to the right of each chart, which gives you a bar plot that tells you which of the variables that are being input into the soft sensor are most influential in producing an outlier if you do find an outlier. Okay, and in the case of the bottom chart there, that blue dot, the circled one, is the current data point, and that seems to be related to NH4 levels in tank 4 in this process, influent flows and RAS flows. Okay, so that brings us to conclusions. I know I went pretty quickly, but I was trying to make sure I fit everything into this time slot. So some takeaways for you if you're looking to maybe think about this or try some of these methods for yourself. I would suggest that application of fault detection and predictive modeling are best done with software support. I would not stop at the algorithm. I would always look past that and look at the integration into your existing system, especially through useful interfaces, to see how this can be actually brought to bear and to provide value in daily operation. Okay, and that the algorithms should be presented to non-expert users, especially for something like, say, controller tuning, that could be done by non-experts if needed. Okay. All right, so I think that's it for me. If you guys have any questions, I'd be happy to discuss them with you.
Yeah, we have, thanks, Ivan. We have already one question. This was posted on the fault detection section. Have you run this? Is it possible to run this on all historian data regularly to ensure good quality data?
You can do this in various ways. If you want to look at it in terms of running on a historian, you could look at installing something like this onto your calculation module that might look at certain variables in your historian, or the whole thing. It depends on what you're interested in, and you could look at it moving forward, or you could backcast it and then have it process data that you already have existing in your historian. So it depends on how what you're really looking for, but I would say yes, it depends on the data and the information content in them. But I don't see why you couldn't apply it to an entire historian.
Yeah, please post your questions into the chat window, and then I will read them and Ivan will answer that. Maybe in addition to Ivan's response, important is that, that's our vision at least, is that you do the data quality analysis online, right? So everyone knows the struggles to get through an existing data set measured a year or 2 or 3 years ago. Yeah. So, and then there's no way to fix an instrument, for example, right? So you do the best you can to somehow reconcile a data set. Our goal is not to be reconciling data anymore. So make sure that the data quality is checked online on the spot, and that any issues are solved as soon as possible. Okay, so there's another question. Can the plant operators control ops control after training?
I would say yes, that is exactly the goal. So you may want to limit some functionality for certain users that could be, you know, password protected. So you may want to have some people doing tuning or being in charge of tuning. Other people may be in charge of sensors and that sort of thing. But generally speaking, yes, that's the main goal of this, is to put this into the hands of non-experts, in the sense of you don't have to be a control expert on any kind of a control structure to be able to understand that the controller needs attention, or that a sensor needs attention. And then with the guidance from the software, you would get an indication of what you should do, how you should perform the checks, and sort of like a guided approach through messages and on-screen prompts on how to handle a certain problem, and then also integrate that with, you know, access to people who have maybe a deeper knowledge of each of the pieces of equipment, or a controller, or whatever it is, that you may be able to contact them and call them for support if you need it. Yeah.
Yeah, so I think the most important thing for us is actually visualization. We pair that with smart tools in the background, but really the focus is here to bring, so Gustav, who's on that call, always calls that the hidden technology. So if it works, nobody cares, and if it doesn't work, everyone is blaming the controls. So the idea here is to bring that to light in a way that you can easily understand that. So just these donuts, they look pretty straightforward. We spend a lot of time figuring out a way to display things so that people understand that DO control is not just one control loop, that there's a cascade and that it works together with other controls. So that is clearly a focus, and hopefully this is something operators are appreciating and learn from it, and have the means to actually properly operate these systems. Okay, so we have another question. Can you comment on the relevance of cybersecurity here?
This could be applied in different sort of levels, or a different scope. It's capable of doing this locally behind your firewalls with no internet access at all. So it'd be completely contained inside of your plant network with no external access. It could be done that way. The preferred way would be that you might give temporary access or access through a VPN to someone who has to work with the software or maintain it remotely, and then you could also apply it through the cloud. So security is part of the design, and it is certainly on our mind when we do an application of it, and we believe that we've addressed that fairly well, actually.
Yeah, so in our opinion, these platforms have to run first on site, because we are actually writing or overwriting controls, right? So and that means we need to have write access. So that's on site within the firewalls. But we typically synchronize with the cloud, or provide access, only read access. to the outside, so that you can check the performance on your smartphone or on your computer. But cybersecurity is, of course, a big concern. I think we found ways to protect the system and make sure that you have a nice overview of what's going on, but not necessarily allow anybody to interfere with your operation from the outside. Good. We have some more time for some more questions. I know it's end of the week, but that's your chance. Okay, keep posting, so otherwise I talk. So if you are not asking, that's my turn. Maybe a little bit more on the controller performance thing. Oh, there is a question. I know InCTRL also do digital twin. If there is a wet weather, does that mean the plan can operate automatically? Do you want to take that, or?
I'm not sure what you mean by operate automatically in terms of, like, are you saying that can these systems compensate for different weather conditions? Yeah, they can. The one thing that that we're looking at here is being able to monitor performance of the controllers and actually suggest for you different tuning for different weather conditions. For example, if you know that you're going to have sustained wet weather, you should perhaps think about your controllers maybe being retuned temporarily to account for that, or you compensating for that if you know it's coming. So in that respect, I would say definitely yes. I'm not sure really how the digital twin fits into this. Like, I don't know if you can answer that live, but.
Yeah, so first thing is, yes, we do digital twins, and with our partners in Germany, they actually started to, it was not called that at that time, but they started to do that in the mid-90s already, with plenty of full-scale implementations. Through Ops Control, one of the modules we have is the ability to link a SimmerSharp model. So that would be a mechanistic digital twin. What we also do quite a bit now is that we set up a data-driven model. These data-driven models have certain advantages, of course also disadvantages, but for me the main advantage here is that they are much more robust against faulty data inputs. So we do both, and then depending on the goals, we do predictions based on that. Wet weather might be one thing to look into, but yes, we can clearly do that. Good. I would say, yeah. Oh, that's good. So the next question. So the software can automatically give suggestion to run the plant, or operator needs to input some info to the software. So we can do both. In our opinion, we are mainly process engineers at InCTRL, and we understand how wastewater treatment works. So we are not convinced that anything labeled artificial intelligence is helping too much. I saw really bad results coming out. We have the input data correct. So that's the main thing to do. Make sure that your data, whatever you do with monitoring and giving decision support, or doing any type of automated control or optimization, the data has to be correct, right? So we build that solid foundation first, and then we apply all these solutions. To be honest, there's lots of room for improved classic PID type control, right? So if you do that properly, and we believe with our tools and our knowledge, we can make that work. That gets you a long way, right? So if you want to get to digital twins, the whole system becomes much more complex, and you have to decide if that complexity really gets you a benefit. right? So we are quite careful. We love to do model-based control, and we do that. But I would say that's something to discuss with the plant, and I like to go step by step and make sure that I take the operators with me and make sure they understand what's going on. We visualize in a way that they can understand that, and then we can basically go step by step into maybe even model-based predictive control or digital twin-based control. Good. With that, I would say we close that 2-hour webinar. Thank you so much for joining. We will send out an email with a link to the recordings as soon as we have that edited and put on our YouTube channel. Thank you so much for joining.
Thank you very much.
Thanks for joining, Gustav. It's an honor.